Okay, to make sense of the equation we derived from previous video, so think about 2 points in space. Okay, the first one, this is my initial point and this is where I begin, and the coordinates are xi, yi, and zi, and I have the final point, so the coordinates are x final, y final, and z final. Okay, so I am going from initial to final point, and there is an electric field everywhere in this region, and I know that how the electric field behaves. Okay, so that means I know about the electric field. Okay, and I want to figure out the potential difference. Is the potential at a given point. Let's say I want to figure out the potential at this point, which is V final, and the initial point, it has potential Vi. First of all, I have to come up with a coordinate system, and this is my coordinate system for that. Okay, this is my x direction, and this is my y direction, and the z direction is basically coming out from the board. This is my z direction. Okay, to get the potential calculated at this point, what I need to do is that I need to evaluate this integral. To evaluate that integral, so I have to get the dot product of E and ds. Okay, so initial to final E dot ds. Okay, so now here E is a vector and it has components in the x direction, y direction, and the z direction. Okay, so I can expand the dot product. So x initial to x final, ex dx minus y initial to y final, ey dy minus z initial to z final. See this thing. Okay, now you got to be careful, so you have to think about the direction of the electric field in each component. If the x component, since I am going from initial to final in that direction, so when I go from left to right in the x direction, if the electric field Ex points toward the x direction, or positive x direction, electric field is positive. And if some reason, if the electric field is directed in the negative x direction, so you have to put a negative sign there in order to evaluate the integral correct. Okay, and the same way is true for Ey. When you go along the y direction, if the electric field is directed in the positive y direction, so the electric field is positive, so the integral is as it is. And if the electric field points downward direction, so you have to put a negative sign for the electric field. The same is true for z direction as well. Okay, so keep in mind, so when you evaluate these integrals, so you have to play with direction. Another trick to use that, so you can get rid of this minus sign. So by switching the limits of the integral, instead of going from initial to final, so you can go from final to initial, and then you can switch this sign here. Okay, so from the next few slides, so I'll be describing several examples, and when we do this example, I think that you will get good understanding about how to calculate the electric potential at a given point once the electric field everywhere in space is known. Okay, and you need to know the electric field completely, otherwise that you cannot make use this equation to evaluate the electric potential at a given point. So very often, so we assign a value for Vi, so it's to be 0. You have to give the potential with respect to your reference. It is very important to understand that. So what really matters at the end is the potential difference, not just the potential alone. Okay? Electric potential around a point charge. We already know the answer for this question because we did that before. But I'm going to utilize the equation that we developed in the previous lecture to figure out the electric potential using the electric field. And I have considered a point charge located at origin, and I consider the spherical symmetry of the electric field, and I use the spherical polar coordinates, and only the R component of the electric field is non-zero, and the R component of the electric field is given by this equation, and everybody knows about it, 4 pi epsilon naught R squared. Okay, so now I have a reference point located at the infinity and where the potential is zero, and the final point is the point that where I want to figure out the electric field, so which is R distance away from the source charge. And write down the equation, which is delta V is equal to minus the integral of f dot E dot dr. So instead of writing the dot product, since I am considering only the R component, I can easily write that ER multiplied by dr, and I'm going from infinity to R. Okay, so instead of delta V, now I can write down V at R minus V at infinity. So that is my potential difference, and which is equal to minus ER. Instead of going from infinity to R, I can go from R to infinity. Okay, I can go from R to infinity and make the integral positive, and can write down the integral this way. Okay, since this is zero by definition, so the potential at R distance away from the source charge now is given by R to infinity, and ER is Q divided by 4 pi epsilon naught R squared times dr. And if you do this integration, and it's a very simple integral, and you can evaluate it to be, now the VR can be written as Q divided by 4 pi epsilon naught 1 over R. So we already know this answer, but you see that you can get the answer quite easily. This is another application of the equation which connect electric potential and the electric field. Okay, here we are going to calculate the electric potential inside a parallel plate capacitor, and again we know the electric field everywhere inside the capacitor, and then we can find out the electric potential using the electric field. Okay, so we have a parallel plate to the left, and which is negatively charged, and another parallel plate to the right which is positively charged. This is obviously 1D, so when you go along the x direction, potential changes, but in the y direction, so there is no change in potential, so it's the same potential everywhere, so we know about that. And let us write down, so at x is equal to 0, we assign the potential to be 0. Okay, so that is my reference potential. So with reference to 0 potential, I can evaluate the potential at x here. Okay, so Vx minus V 0 is given by minus, the electric field has only x component, so there is no other components. So the electric field has only the x component, and all other components are 0, and because of that I can write down it's just Ex, and other components are 0, and it's Ex dx, and going from x initial to x final, but the x initial is 0 and x final is going to be simply x now. Okay, now you remember that you got to pay attention to the direction of the electric field when you evaluate this integral, and here the electric field is in the negative x direction, so you have to substitute the electric field with the negative sign, so that gives us minus 0 to x. Instead of Ex, now it is Q divided by epsilon naught A with the minus sign, so that's a constant, and dx. Okay, so it's simply qx divided by epsilon naught a, qx divided by epsilon naught a, or it is ex as we know. Okay, so the electric potential Vx is a linear function, and the potential is 0 at the negative plate. At the positive plate it is having the maximum potential. Okay, so the maximum potential is E times d, where d is the distance between the plate.